So we talked in class today about using the factor theorem, and we used the factor theorem to determine whether or not a divisor was a factor of a polynomial. That is, that it divided into it cleanly without any remainders. And we're going to use the factor theorem today to completely factor a polynomial. First, why are we doing this? Well, if you remember, the whole idea behind this is that if we were going to graph a polynomial, it's a lot easier to graph a polynomial in factored form than it is in standard form. So what factoring allows us to do is to change a polynomial from standard form into factored form. And once it's in factored form, then what we can do is we can determine what the zeros are and what the behavior is around the zeros, and we're able to graph the polynomial. So that's the reason why we're doing all this. Okay, so we'll start off with an example. So for example, let's say that I've been asked to factor the following polynomial: x cubed minus 19x plus 30. And what I'm trying to do is I'm trying to get this into the form of factors so that everything is in brackets. Now, because this is a third degree polynomial, I'm going to have 3 sets of brackets when this is finally all factored and done with. And then I'm going to be able to recognize what the zeros are. But I don't want to use the factor theorem and sub in every single value that there is for x. What I do know is that, and we'll use a different pen for this. Let's use purple. I know that the value at the end of the first bracket and the end of the second bracket and the end of the third bracket are eventually all going to have to multiply together to give me this constant value in my polynomial. So in other words, I know that the values I'm going to determine to use the factor theorem have to be factors of, in this case, 30. So let's talk about the factors of 30. So there's a lot of them. We could have plus or minus 1, plus or minus 2, plus or minus 3, but 30 doesn't divide by 4. So we're not going to have plus or minus 4. We could have plus or minus 5. We're going to keep going, plus or minus 6. We don't have 7. 30 doesn't divide by 7, doesn't divide by 8, doesn't divide by 9, and plus or minus 10. And that gives us a good bunch of numbers that we can start off with to try out our factor theorem. So let's get going and use the factor theorem to see where this all turns out. So the first thing that I'm going to do, is I'm going to let p at x represent this polynomial, x cubed minus 19x plus 30. And then I'm going to one at a time sub in the factors that we figured out for the factors of 30. I'm going to sub them in to figure out which factor is going to give me a value of 0. Our goal is to find out what I can plug in there for x to get no remainder, because that's going to tell me that that becomes a factor. All right, so let's start off with 1. If I have p at 1, then I'm going to have 1 cubed minus 19 times 1 plus 30. And you guys can tell me already that you know that that is not going to equal 0. So then we try p at negative 1. So that's going to be negative 1 cubed minus 19 times negative 1 plus 30. And again, if I do the math, that's going to be negative 1 plus 19 plus 30, and that also doesn't give me 0. So neither 1 nor negative 1 are factors of this polynomial, this particular polynomial here. Okay, so let's try 2. So I'm going to plug in 2. So that's going to give me 2 cubed minus 19 times 2 plus 30. And if you do the math on that, you're going to get 8 minus 19 times 2 plus 30, and you are going to get a value of 0. All right, so then what this is telling us is that, therefore, we know that x minus the k value, so 2 is our k value, so the k value is equal to 2, so therefore I know that x minus 2 is a factor of this particular polynomial, x cubed minus 19x plus 30. Okay, so that's exciting. Where does it take us? So since we know that x minus 2 is a factor of it, let's see if we can figure out the other factors. And we're going to do that by using synthetic division. All right, so synthetic division again. We're going to write down all the leading coefficients of our original polynomial. So in this case, I'm going to have a 1. Now notice I have a missing term here, a missing x squared, so I have to put in a 0 for a dummy term. Then I have negative 19, and then I have 30. Right? Now, x minus 2 is a factor. That means my k value is positive 2, so the 2 goes there, and we drop the 1 down, and now we do our multiplying. So 2 times 1 is 2. We add 0 plus 2 to give us 2. 2 times 2 is 4. Again, whoops, we add negative 19 plus 4, which gives us negative 15. And 2 times negative 15 is negative 30, and that's going to give us 0. And if you did this part right up here, if you did the factor theorem right, then you are going to end up with this 0 here with no remainder. Because that means, oops, sorry, no remainder is what I was trying to write there. Because that means that this is a factor. Okay, so therefore, this is what I know. I know that my polynomial can be written as x minus 2, because that was one of the factors, times all of this in here. And because this was a cubed, this was a degree 3, when I did the synthetic, it's going to go drop down a degree, and it's going to become x squared plus 2x minus 15. All right, so we're well on our way. We have one of our zeros here, but this one here is not completely factored. But hey, we can do this. This is easy stuff. This was grade 10 stuff. This is factoring a simple trinomial. So if I'm going to continue this on, it's going to be x minus 2, and then I ask myself, oh yeah, factoring a simple trinomial, what multiplies to negative 15 and at the same time adds to positive 2? So let's see, what multiplies to negative 15 adds to positive 2. So that's going to be x plus 5 and x minus 3. Minus 3 times 5 gives me negative 15. Minus 3 plus 5 gives me positive 2. And at this point, I've got 1, 2, 3 brackets. So that makes sense. It's a third degree polynomial. And I've got zeros at 2, negative 5, negative 3.